Good day. Today, we will be presenting on the 1940 Tacoma Narrows Bridge collapse. Before we begin, here are our group members.
The contents that we will cover for our case study, which is the Tacoma Narrows Bridge collapse, are presented here. So moving to the first chapter, which is the introduction part. So it's below structural failure happen between the environmental and design interaction. So as we all know, large infrastructure often face wind, temperature changes, seismic event, which can lead to unexpected dynamic effects. Therefore, the vibration may go to agitation, pushing structure beyond design limits. Note on that the design choices to save cost or reduce weight can reduce stiffness and also the damping, making the structure become more vulnerable. So this past failure actually show the need to design for dynamic behavior and include redundancy, not just static strength. For the overview of the Tacoma Narrows Bridge incident that happened in 1940, from Figure 1 it showed the Tacoma Narrows Bridge on its opening date. Meanwhile, for Figure 2, the overview of the collapse of the Tacoma Narrows Bridge exactly happened 4 months later after its opening.
The collapse of the Tacoma Narrows Bridge in 1940 is one of the most studied structural failures in engineering history and continues to serve as a critical learning point for civil and structural engineering worldwide. The bridge, located in Washington State, USA, was designed to span the Tacoma Narrows Strait of Puget Sound and opened to traffic on July 1, 1940. The Tacoma Narrows Bridge featured an innovative yet problematic design. In order to reduce costs and minimize material usage, the bridge was constructed with a relatively narrow deck, only 12 meters wide, and shallow the flat girders instead of the deep thrusters, which had been commonly used to add rigidity to large suspension bridge.
Chapter 3 outlines the key technical reasons behind the Tacoma Narrows Bridge collapse in 1940. Although innovative, the bridge failed due to serious design flaws. These include aerodynamic instability, lack of structural stiffness, and poor risk handling, each violating key sections of the Engineers Act 1967. The first issue here was the aeroelastic flutter, where steady wind caused violent twisting. It was neither predicted nor tested, violating Section 8(1)(b) on due diligence. Next, the bridge's shallow girders led to poor torsional stiffness, making it overly flexible, earning the nickname of galloping girty. This breached Section 8(1)(c) on structural safety. Lastly, early warning signs were overlooked and no expert consultation took place, violating Section 7(b) on public safety responsibility. The figure here illustrates how increased wind speed caused negative damping and instability, stressing the need for proper aerodynamic analysis.
So we often hear about the Tacoma Narrows Bridge as a physics case resonance, vibration, torsional flutter. But today, I will walk you through why it is also an ethical failure. Decisions were made that put people at risk, bypass proper engineering judgment, and ignore history. These failures broke the very principles we are expected to uphold as engineers. These are the 3 ethical issues that led to the collapse. First, public safety was sacrificed for aesthetics and budget, a direct violation of BM's code. Second, the design was based on unproven theory without proper testing, which falls outside professional competence. And lastly, engineers ignored lessons from history, showing a dangerous lack of accountability. These weren't just technical errors, they were ethical failures.
Tacoma's collapse revealed 2 gaps: aerodynamic understanding and also professional accountability. Building solutions like wind tunnel testing and safety simulations now predict dynamic loads, but Malaysia's Engineers Act made this effective through Section 10(b)'s the accredited checkers and also Section 7(1)(e)'s the certification requirements. Hence, we can say that technology will find risk, while the regulations will ensure we, the Engineers Act, accordingly and appropriate. True safety comes from integration. Our sensors detect vibrations, but only certified engineers under Section 41(e)(c) interpret them. Peer reviews validate every safety model. Where Tacoma had imbalance, we now have system checks at every stage, and this is how modern engineering prevents failures.
In conclusion, the collapse of the 1940 Tacoma Bridge marked a turning point in structural engineering because it showed the consequence of prioritizing cost and aesthetic over safety. So this will lead to major changes in engineering practice and a stronger regulation like the Legislation of Engineering Act 1967. Ultimately, this case reminds all of the engineers of their responsibilities to combine technical expertise with ethical commitment to ensuring safer and more resilient structure for the future. So that's all for our presentation. Thank you.